Have you ever watched a ballerina turn and felt like you were witnessing the impossible? A flawless pirouette balanced on the tiny platform of a point shoe, a body spinning so fast it almost blurs, and then somehow stopping with absolute precision as if physics itself agreed to take a brief pause. It feels like pure magic. But here's the incredible part. It isn't magic at all. The same physical law that governs a ballet dancer's pirouette also controls spinning planets, figure skaters, and even massive rotating storms like tornadoes and hurricanes. Beneath all the artistry, elegance, and emotion is an intense negotiation with the laws of physics. Every turn a dancer performs is a carefully controlled battle between balance, momentum, force, and timing. And once you understand the science behind it, pirouettes somehow become even more impressive because a ballet dancer isn't defying physics, they're mastering it. Caroline Simpkins. I'm a former professional ballerina with a PhD in biomechanics, and today we're looking at the science of pirouettes in ballet. To understand how a ballet dancer does this, let's think about an ice skater. We've all seen it. The skater is turning with their arms out, they pull their arms in, and suddenly their turn gets crazy fast. This isn't a trick. It's a perfect demonstration of one of the most fundamental principles in physics, the conservation of angular momentum. In simple terms, this law says that an object's spinning energy stays constant unless an outside force gets involved. A ballet dancer is essentially a master manipulator of this very principle. Every turn is a hard-won victory over the laws of physics. So what is angular momentum? Think of it as momentum, but for spinning. An object moving in a straight line has linear momentum. An object turning in place has angular momentum, and this depends on three things: its mass, how fast it's turning, and this is the big one, how that mass is spread out. This distribution of mass is called the moment of inertia. And here's the key: a large moment of inertia, when mass is spread far from the center, like a dancer with their arms and legs out, makes it harder to turn. A small moment of inertia, when mass is pulled in tight, makes it easier to turn faster. The law of conservation of angular momentum means there's a trade-off. Since the total amount of rotation wants to stay the same, if you decreased your moment of inertia, your rotational speed has to increase to make up for it. When a dancer snaps their arms and their leg in close to their body, they are radically shrinking their moment of inertia. The dancer's turn has no choice but to get faster. To the dancer, this acceleration can feel almost instantaneous, as if the turn suddenly takes off the moment everything pulls inward. This is the secret to a pirouette's speed. It's not about pushing harder, it's about starting with a certain amount of rotation and then expertly changing the body's shape to control the speed. But before a dancer can control their turn, they have to create it. A pirouette doesn't just happen, it starts with a powerful hidden force called torque. Torque is just a twisting force. If you've ever used a wrench on a bolt, you've used torque. For a ballerina, the floor is her wrench. The turn starts in the preparation, the plie, a deep knee bend. From this crouched position, the dancer pushes against the floor. Thanks to Newton's third law of motion, for every action there is an equal and opposite reaction, the floor pushes right back. By pushing at just the right angle, the dancer turns this straight push from the floor into a rotational force, torque, that gets their body turning. And importantly, most of the dancer's angular momentum is generated right here during the push-off. Once the dancer rises onto releve or point and the turn is underway, they are no longer creating much new rotational force. Instead, they're managing and conserving the momentum they already generated. The dancer's arms are also key for generating that initial torque. As they spring into the turn, they snap them from an opening position into a tight, controlled one. Now, this isn't just for looks. Bringing the arms inward helps conserve and amplify the rotational speed already generated during the push-off. By pulling mass closer to the center of the body, the dancer decreases their moment of inertia, allowing the turn to accelerate dramatically. It's a beautifully coordinated explosion of movement, all designed to create the maximum torque to ignite the turn. So once the turn starts, physics takes the wheel, but it's the dancer's technique that pilots the ship. Their body must become a perfectly balanced, rigid column. The most iconic part of the posture is the Passé position, where one foot is drawn up to the knee. This isn't just for looks, it's a physical necessity. By bringing the mass of their free leg in close, the dancer pulls that weight towards their central rotational axis. As we know, this dramatically reduces the dancer's moment of inertia, causing that brilliant acceleration. Now, maintaining that turn requires incredible stability. The dancer's center of gravity has to stay directly over their tiny base of support, which in this case is the ball of the foot or the tip of a point shoe. This takes immense core strength to keep your torso, hips, and shoulders locked in a straight line. The slightest wobble can throw the whole thing off and end the turn. And then there's spotting. You've probably seen a dancer's head whip around, seemingly out of sync with their body. That's spotting. The technique involves fixing the eyes on a single point. As the body turns, the head stays behind, looking at the spot for as long as possible. Then, with a flick of the neck, the head whips around to find the same spot again. This clever trick does two things. It helps prevent dizziness, and it gives the dancer a constant reference point to maintain balance and control. So if angular momentum is conserved, why does a dancer ever stop turning? In one word, friction. There's friction from the floor and also slight air resistance pushing against their body. These forces are constantly trying to steal the dancer's momentum. For one or two pirouettes, the initial torque is usually enough. But for one of ballet's most dazzling feats, the 32 fouettés turns from the Black Swan pas de deux in Swan Lake, the dancer has to fight back. The word fouetté is French for whipped, and that's exactly what's happening. A fouetté isn't one long turn, it's a series of individual turns, each powered by a fresh injection of torque. At the end of each rotation, the dancer briefly extends her free leg to the side, which momentarily slows her down. Then she whips the leg back into the passé position. This whipping motion, combined with a tiny push from her supporting foot, generates a new burst of torque, refueling the momentum lost to friction and allowing her to rotate again. So in Swan Lake, as well as many other ballets, this happens 32 times. Each turn is a miniature physics lesson. Extend a limb to control the turn, then whip it back in to power the next rotation. It's a breathtaking display of stamina and precision, a constant battle against friction, won again and again through pure technique. So the perfect pirouette isn't just beautiful, it's a masterful application of physics. Every turn is a delicate balance of generating force, managing momentum, and battling friction. The initial push-off provides the torque, changing the body's shape controls the speed, and the conservation of angular momentum creates the magic. Thank you again for tuning in, and I look forward to seeing you next time on the Ballet Science Podcast.